All right, Ed, take it away.
Hello, everyone. I am Ed Barker. I am, this is my 16th year. Hang on one second here. This is my 16th year of being part of the first robotics competition. I'm an electrical engineer. And as soon as I can find my presentation here, I'll get this show on the road. So let me tell you a little bit about where I've been and what I do. I grew up in South Carolina, and then I went to the University of South Carolina, got a Bachelor's of Science electrical and computer engineering. Worked in Washington, D.C. for a while. Anyway, I came back to Atlanta, started working here. Got a Master's of Science in Public Policy at Georgia Tech. Also in the Ivan Allen College of Liberal Arts at Georgia Tech, on HTS studies. I'm also with Kennesaw State University College of Engineering, working on STEM outreach, particularly to first students. And Tech won a football game, I think, yesterday. I'm not sure. I work for L3 Harris. L3 Harris, as in this form, has been around for just over a year. The Harris Company's been around for, I think, maybe 130 years. L3, I'm not so sure. Those two companies merged together a little over a year ago. We've got 48,000 employees. One of the things that makes L3 Harris, one of the many things, very distinctive and different, is that we have over 20,000 scientists and engineers. And as a percentage of the population of the company, that's a very, very high number. We're a very intensive research and development oriented company. We're in a lot of sectors. And I'm just going to barely be able to scratch all the different areas that we do because we do so much stuff. We've got over 3,000 patents awarded to the company over time. So I'll just want to give you a smattering of some of the things that we do here at L3 Harris. We do universe exploration. We support all sorts of activities in the exploration of the universe, from ground-based observatories to deep space. We do optical systems for telescopes, ground and solar. I'm going to be jumping around a lot here. I'm just going to be like popcorn going all over the place. There's something called the Deep Space Network. We're part of operating and developing the Deep Space Network. It's been around since at least the 1960s. The Deep Space Network was necessary for being able to communicate to the astronauts when they went to the moon. The further, just like if you light a candle and you start walking away from it, the further away you get, the dimmer it gets. Radio signals are the same way. So it takes very, very big antennas to pick up very weak signals for satellites and spacecraft the further and further away they get from Earth. One problem with trying to talk to anything in space, like something going to Mars or Moon or just anywhere in deep space, is this Earth that we live on has a silly habit of keep spinning and rotating. So everything in the sky is moving. And if you've got to fixate on an object in the sky, you've got to solve the problem. And the way they did that was it's called the Deep Space Network. There are 3 sites in the world: Madrid, Canberra, Australia, and Goldstone, California. And each site those 3 sites have 24 dishes that hook into deep space and enable our communications to things like the Mars rover. This is an example of a big satellite dish here, or not satellite dish. It can be going to a spacecraft for many things. We also supplied components to the James Webb Telescope. You've heard of the Hubble telescope. It's been around for over 20 years. The next generation, really the upgrade to the Hubble telescope, is the James Webb Telescope. And I just saw this week that it's checking out very, very, very well. So hopefully it won't be long before we see it go up. You see this segmented primary mirror here. There's L3 Harris personnel attending to it here. If you look in the top center of the photograph, near the very top center, you'll see somebody in a white suit. If you look on the upper left-hand corner, you'll see somebody in a white suit up on a man lift. So that's a big optical mirror. And that thing, we have to get it all together and get that up into space. After the James Webb Telescope, you're going to see another telescope come out called the Wide Field Telescope. Telescopes are designed and built for different tasks and orientations. And this is a work that's in progress. Hopefully, it won't be too long before it gets up. Here you can see Some of it sitting right here on this platform in the assembly area. This is a satellite that just went up just very, very recently. This is for the Air Force. It's some sort of information gathering radio signal satellite. I'm not sure exactly what they do with it. If you don't like space, we got things a little closer to Earth. We have teams of people working on autonomous robotic ships. More and more, you're starting to see a convergence between robots and things that we used to do in cars, planes, trains, ships, and everything else. You've heard of autonomous automobiles. You're going to see more and more autonomous aircraft. We have autonomous robotic ships that are being developed. And if the ships are too big, you can do something a little smaller. We have surface craft here that's much smaller. This is another project for someone that the company did. And if being on top of the water is too boring for you, you can go underwater. We have underwater robotics also. There's a lot of opportunities here, from deep space to near space to on top of the water, in the water, under the water. And here's a public safety. There's a public safety issue here. There's a robot driving around getting ready to open the trunk on a car and retain some sort of problem. If you don't want to do that, we have spaceport operations. We have spaceport operations on West Coast, East Coast, I think some other places around. You can get an operational side, you can get a design side, test side, all sorts of engineering, electrical, mechanical, chemical, industrial. I'm sure everyone is familiar with their GPS. Everyone has a phone. It's always telling you where you are. The way that works is something called GPS. The GPS system is a constellation of satellites that constantly circle the Earth. They transmit what's called timing information. Knowing the timing information and the position of the satellites in the sky, the GPS will calculate exactly where you are to within not too many feet. It was originally developed for the military back 30 or 40 years ago, and now it's used for just about everything, non-military applications. Here you can see a picture from space. Florida at nighttime, you can see the Orlando area all lit up. The Miami coast, southeast coast of Florida is all lit up nice and bright. If you're careful from the big lake in the middle of Florida, kind of going up, you kind of see this little ribbon of light that goes up through central Florida. It's it's one of the interstates. Goes up through Orlando, makes its way up into Georgia, through Valdosta, keeps on going to Atlanta. You can see the East Coast lit up with the little houses and stuff up and down the coast. To the right, there's a large hurricane, and embedded in the hurricane, you'll see some lightning flashes going off with some very large thunderstorms. So where did those images come from? They came from things like this GOES imager. I can't remember what GOES stands for, but it has to do with weather observation, Earth observation. That's an imager. So just think for a minute about how big do you think this item is? The next picture, you're going to see it. It's going to be rotated 90 degrees standing upward. And just to the right, you'll see a man there for scale. So that's actually a pretty big item. And that item is the Advanced Baseline Imager. It not only sees visible light, it sees all sorts of spectrums of UV lights, long-range UV, short-range UV. It's all over the electromagnetic spectrum. Sends a lot of data feeds back down to the ground with this information. And here's the satellite here. On the far left, you'll see this big rectangular thing. Those are the solar panels that's used to power the spacecraft. And once it launches, well, before we go next, look at the very bottom right of the corner, you'll see a man standing there in a white suit. So that's a big piece of equipment. So anyway, you see the solar panels. You go to the next page. Then they launched the satellite. I think it went up on an Atlas launch vehicle. They'll park it in what's called geosynchronous orbit. It stays in that position right there relative to the image that you see on Earth forever, close to ever as we care for it to be, about 23,000 some odd miles up. And you can see the solar panels that are unfurled and extended. And that's what it looks like when it's on station. This is an artist image. So it's collecting a lot of data. Where does the data go? It has to come back down to the ground. L3 Harris, we work on the GOAS Communications Data Network, which is situated at Fairmont, West Virginia, Suitland, Maryland, and Wallops, Virginia. These ground stations receive large volumes of data from GOAS satellite over the Atlantic and another one on the left side over the Pacific. It takes two satellites to get the coverage that we need to do. I'm going to take a side trip, and then we'll come back to some of the L3 Harris stuff. This picture here is taken when our team went out to Houston, Texas 2 years ago in 2018. We toured the Johnson NASA Space Flight Center. And not only when you go on the tour, one of the things that they warn you about is that this facility, it's a live, active facility. This is actually this tech support area for the International Space Station, which runs 24 hours a day. In here, the upper right, you'll see hanging from the wall a small scale model of the ISS, the International Space Station. All these modules off to the right are modules that are on station. This exact replicas of what's in space. Lower left, you'll see some real space suits. They look like sort of mock-ups, but they're the real deal. Everything in this room is real. This is a real tech support area. You'll see the nose portion of the space shuttle, and all this room was for training and for technical support. If you were to stand at the spot and turn to the left, look kind of straight ahead, just off to the bottom left, you'll see something called the Boeing Starliner spacecraft. Kind of in the middle to the right, you'll see the Orion spacecraft by Lockheed Martin. The Orion is designated to go to deep space travel. It's being designed and configured to go to do trips like to the moon, the next manned mission to the moon. Now, I'm going to see if you can spot something here. Look in the upper left edge of the picture. Look up above the Starliner spacecraft. Keep looking up, up, and see if you can spot a first blue banner, first robotics competition blue banner. And if you look a little further over this piece of space station, look off in the distance to the left, you'll see some more blue banners. Then you'll see right on the blue banners, you'll see some blue cabinets. And there you go. Those blue cabinets on the right-hand side form a wall between the ISS area and a robotics team called the Robonauts. I think they're team number 118. If you look on top of the blue cabinets on the right, you'll see some old robots from the past just stacked on top of it for display. On the far wall, you'll see blue banners. Right below the banners on top of those blue cabinets, you'll see trophies and plaques of trophies and things and stuff. Right in the middle of the picture, you'll see they have a full-size field, and your shop is off to the left. So that's a really cool looking workshop. I just wanted to kind of show you that there's a lot of aerospace companies involved with the ISS and the space program and aerospace and all the rest. But what you're seeing here, the Orion spacecraft that you saw off in the previous pictures, this is an artist's rendition of what it will look like when it's in orbit around the Earth and getting ready to go to a destination like the moon. I believe that lower portion of the spacecraft, I think, is actually produced by the European Space Agency. That's kind of new. It's called the service module. And the conical shaped part people live is the command module, very similar to the Apollo program. This is just one of the items we're putting on the Orion spacecraft, and the audio communication systems, interiors. There's a bunch more equipment too. There's VHF, UHF, S-band radios. I don't know if they have any L-band, but there's a lot that goes into making a manned spacecraft. Some of you watching this may be familiar with the CAN bus communications that's on the FRC robots. CAN bus actually came from, I think it was originally designed for the automotive industry. It's what runs cars. It also runs the London subway. But about 2 or 3 years ago, CAN bus became approved for space flight, and it can be used on smaller and medium-sized satellites. This is the chip from the Intercell Corporation. Now all electronics that goes into space has to be radiation tolerant because it's a very hostile environment, and radiation there can destroy the semiconductors that you typically see in a ground-based situation. I'm not sure if this is L3 Harris cockpit or not, but the reason I have this picture here is I wanted you to see the cockpit. If you look in the picture of any aircraft from a couple of decades ago or before, there were many analog instruments, analog dials, analog gauges, kind of like your grandfather's automobile, your grandfather's airplane. Today we have what's called glass cockpits. We have these super aerospace grade displays, components. We design and build these units that go into the dash. You see buttons, you see touchscreen screens, high resolution screens are high reliability. They're tested to extremely exacting standards for space and airborne use. And the group I'm in at L3 Harris, we do a lot of this. And as a matter of fact, that group is in Alpharetta, Georgia. This is an example of a product that come out of Alpharetta, Georgia. This is a panoramic cockpit display. I want to show you this interior here. We didn't do this, but this is the Orion spacecraft. This is a mock-up out on the West Coast. And if you look up at the top half of the picture, you'll see display systems, buttons, controls, and stuff. And they look pretty much identical to what you saw in the prior picture of the commercial aircraft. For a lot of things, there's a lot of similarity, close coupling between what we do in spacecraft and what we do in commercial and military aircraft. Again, we didn't do this equipment either, but what you'll see here on the top, again, that's the Orion dashboard. And then the bottom half is the SpaceX dashboard. It's a little sleeker, a little sleek, I'll put it that way. But one of the differences that you'll notice is the bottom has a lot more touch screen controls assigned to it as opposed to what's up on the top. Even then, the center console of the SpaceX still has buttons and dials. There are people that spend their entire careers doing nothing but studying the interfaces between humans and machines and how you sit down and operate a machine and what should be on a touch display and what should be on a button. You can get a PhD in it, or tech or something. So let's talk about robots for just a moment. This past year, we had the Infinite Recharge game, the 2020 game, the original Infinite Recharge. Now, this year is very different, but there's also an object lesson that we can get to here. You're allowed to upgrade your robot. You can rebuild it, you can upgrade it, you can change it, whatever you need to do to go into the 2021 season. In other words, you can do a technical refresh. Now, it turns out the term technical refresh is actually a real phrase that's in the aerospace industry. It has been for at least a half a century. So just think of you going into next season with technical refresh, number one. And then you come out of the season and you get ready for grits and you can rebuild your robot again. That would be technical refresh number two. And in our business, we call it a TR. So what do I do for a living? My job today, and it will change later, I'm a lead software engineer for the Space and Airborne Systems Division of L3 Harris. And I work on mission bus communications. What does that mean? Just think about the human body for a minute. You have your body, you have your brain, your spinal cord, your nerves, and all at the base of your brain where your spinal cord comes into your brain. You have your neural cortex, and from there, that pretty much calls the shots. That has to work for everything else to work. I work the neural cortex of all this communications and information on that thing. That is the F-35 fighter jet. It's been around for a while. They're looking for it to be around for another 50 years. And the airframe will be common, the engines and stuff, but you're going to see occasional technical refreshes. We are on what's called the F-35 Technical Refresh 3, TR3. That's the program that I'm on. So if the first generation was just F-35, there was refresh 1, refresh 2, refresh 3. This will be the 4th generation of the F-35. And the team I'm working on is we're replacing the computing platforms inside the aircraft and the cockpit display units, and looking to get a 75% cost reduction, but we'll have 25 times more computing power. You can think of this aircraft as having a miniature supercomputer or sub supercomputer that's used to support the aircraft and all the things that it has to do. Used to be, airplanes are pretty simple. You have throttle, stick, engine, airframe, that was about it. Now it's a flying data network and it has lots of sensors, a lot of integration. It's connected. You heard about cloud computing, and a cloud computing in normal person's environment is really just a data center like in across town or something. But this is kind of like cloud computing. It's really in the clouds. Let me go back 1 second. If you look right near, look at what the pilot is staring into on the dashboard there. That box, the first 4 or 5 inches of that display, of that dashboard, it's called the PCD, or panoramic cockpit display. Behind it is another box about the size of a small, probably the size of a milk carton, volumetric, not milk carton, a milk, 2/3 the size of a milk crate, like we used in the game a couple of years ago. This is the display unit. It's 22 inches by, I think, 8 or 10 inches tall. Touch screen. First time I heard a F-35 pilot say the first time he got in the plane and looked at it, says he thought it was like a giant flying iPad. Got a few knobs at the bottom, because sometimes you do need knobs and buttons. But pretty much everything the pilot needs to know is either on this display or can be brought up on it. Touchscreen. This is the computer that's sitting behind it. You can't really see the inside of it. There's a whole bunch of, it's very modular. There's, I think, 8 or 10 modules inside of it. Lots of redundancy. Many different computing systems in it. There's another chassis. This is about the length of a robot chassis. Volumetrically, maybe size of maybe 2.5 milk crates. And it can hold about almost 50, about 4 dozen processor cards. Either one of these cards could be an independent computer or dedicated computer for some other task. All you're seeing here are the aluminum slabs. There's a lot of electronics that goes into it. And this is a very powerful computing platform. And, 30 years ago, you'd never see anything like this on it. 30 years ago, aircraft were all analog, and now they're very complex digital machines. Think for a minute about what this is. 114,000 years. How long is that, and why do I have it on the screen? So you take your robot, you go to competition, you go on the field, and what are you trying to do? You're trying to get connectivity. You're trying to make sure that it's synced up to the field. You're trying to make sure it's running. You run a match for 2.5 minutes, and hopefully you can run the whole match. Your software won't crash. You won't lose communications. The robot won't break, so on and so forth. This is the mean time between failures to the design engineering standards that we have to do for the software for this aircraft. It's called SEAL Level 1 or DAL Level A. It's Design Assurance Level A or Software Engineering Assurance Level 1. They're very similar to about the same thing. And to go for that level, say SEAL Level 1, 114,000 years without failure. It's a long time. There's 4 more levels, 2, 3, 4, and 5. SEAL Level 5 is the pokey stop doesn't work in the back of the plane or your in-flight entertainment crashed and nobody cares. Whereas SEAL Level 1 is the most critical life safety criteria that you have. So that's the group I work in. Work on software for communications buses for these aircraft. And we're looking to get F-35 TR-3 program done, out the door. I'm going to turn it over to Q&A time and stop presenting. I'm looking for questions, comments, whatever you want to do. Hello, Mars, can you hear me?
Yeah, we can hear you.
All right.
Folks, has anyone got any questions for Ed?
I put them all to sleep.
Nope, you've got a question. Do you guys offer any internships?
That's a good question. I wish I had an answer. I'd be surprised if we don't have internships. I know if you've ever heard of the Lockheed Martin Skunk Works, I know the Skunk Works has internships for college students. I think you would almost have to be an undergraduate. I'd almost guarantee that we wouldn't do it for high schoolers, but yes, for undergraduates. And I would be surprised if we didn't. I know Lockheed Martin does. They're our big customer. How did I get interested? Okay. As far as I can remember, it seems like I was always sort of interested in science and technology. Of course, in those days, it was radio because we didn't have science and technology like we did now. So originally, it was like, I think radio was kind of interesting to me. And then the space program, the race to the moon, all that occurred in really my formative years from the time I started, really from when I was in kindergarten through high school. That was the trip to the moon. So there was a lot to absorb. I was intensely connected to that, and I just stayed with it. Does the job take you to many places? Right now, my job takes me nowhere. I am actually, I'm going to move out of the way here. I'm going to just slide around a little bit. So if you look at this office right here, there's 6 screens right there. About 2/3 of that I use for work from home. I am now in a permanent work from home situation. I work on software in a laboratory in Melbourne, Florida, which is on the Space Coast, right next to Cape Canaveral. I do all my software development right here in Kennesaw. I haven't been to Melbourne, Florida in a long time. But certainly in the normal times, I would have a chance to travel, and especially depending on my job, I could travel a lot if I wanted to. It really depends on what part of the business you get into. Right now in my part of the career, I'm pretty happy to sit right here for now. I would like to go down and see some launches though. I have a meeting with my team members, and we're scattered around the country. Most of them's in Florida. We had a meeting that starts at 9 o'clock every morning for about 30 minutes. And everybody came in the meeting excited the other day because on the way, everybody's getting ready to sit down and watch the meeting, and a Falcon Heavy just took off with a whole bunch of satellites for SpaceX, and you heard a double sonic boom out of it. At Lockheed facility, I tell you, you'd have to really look at the Lockheed website to see their internship opportunities. It kind of depends on what you want to do. Michael was asking about specific aircraft. These are big programs. Even engineers rarely actually touch aircraft, especially at Lockheed. They have very highly specialized workers that actually do the aircraft, touch the aircraft and put it together and stuff. You get to touch prototypes and engineering prototypes and mock-ups and that kind of stuff. Production aircraft, it's a little bit different. Internships, it depends whether you're doing software internship. It could be a manufacturing, design, fluid dynamics, industrial engineering. You could be one of 100 different places. Since I'm waiting on another question here, I'll tell you a little bit about this job. I worked in aerospace way back years ago for a long time. Then I left, went to commercial business, and then to Kennesaw State University for 7 years. And then I went back to L3 Harris just not quite a year ago. The round of interviews I had for L3 Harris was really different than anything I've ever experienced. I went through 5 rounds of interviews. Several reasons for that. We're looking for people that have what you might call the right stuff. There's a high level of qualification that you need to have. I mean, we do hire people straight out of college, but we have extremely high standards for life safety and reliability and performance. We also have very high standards for ethics, being able to work under stress where there's project stresses. Let's think about your robot build season. Your robot's going to ship at the end of the build season no matter what. You're going to go to competition on competition day. It could be a box of parts that's going to go. That doesn't work in my business. If there's a problem, you hold it. You have to work the problem. And schedules are pushing and says, we got to get this thing done by a certain date. And if it's not right, then you just say, it's not right. That's a personal warranty. It's a commitment to excellence. It's what our customer demands. It puts pressure on you. But one hand, you got to make schedule. On the other hand, you got to make 0 defects. And the 0 defects are designed in with the front end. Whereas, dealing with a robot, if you got a defect, well, you know what, you'll deal with it when you get back to the pit.
All right, guys, do we have any more questions coming in?
So I'm just curious, sir, the people that's on this call, are they more interested in hardware design or software design? You want to just type into the keyboard what you might be interested in, hardware, software, something else, management, finance, manufacturing, hardware. All right. Hardware, airframe, okay, that's hardware. Super. I know Lockheed, I don't know the statistics, but I know like over here, the various Lockheed facilities, they have a very large number of mechanical engineers. They probably have more mechanical engineers than they have anybody. I think that's what I've heard. Some people want to go and get an aerospace degree, but won't design airplanes. The ability to get a job where you actually design an airplane, that's kind of tough. It's not that often you come out with a new airframe, but they have people in aeronautics and aerospace that do a lot of simulation and design work, especially fluid dynamics, flutter. Like they have people down here in Marietta, that's all they do is something called flutter. A lot of supercomputing, trying to model what happens with airflow. No software people, huh? Software people.
All right, guys, anything else?
Okay, hang on. What technologies could be used in our robots? Tell you what, we're not a big question, but I tell you the thing you really want to do as a high school student, become good at your craft. Learn how to pay attention to details and learn how to think systematically about how you're tackling your problems and solving your problems and making sure that you're solving 3 times more problems than you're creating. You've heard of 2 steps or 1 step forward and 2 back. You're going to have 2 steps forward and 1 back, the worst case. I think developing your skills will be more important than trying to fish out for any technologies beyond what's already available in the FRC space. because when you come in for an interview, we really want to see your ability to really tackle a problem and get on top of it, and wrestle with it, and drive it down to the ground and get it settled.
That list is long.
What? No, that's okay. I graduated at the University of South Carolina with a degree in electrical engineering. Electrical engineering is what I really wanted to do. It's too long a story to go in here to hear, but I began college doing some software stuff, and I wound up becoming very good at it, even though I still wanted to become an electrical engineer. I had to do computer software on and off for various reasons. And then I went and got out of college and went to work for a company called Raytheon Division E-Systems, so the old E-Systems company. We did sensors for spy aircraft, spy satellites, radio systems and stuff. That same facility did a lot of stuff when they went to the moon. I wound up doing about 10 years worth of intensive software development there. And when I left there, I came to 2 other firms, continued to do software development. I wound up doing my career about 90% software development, about 10% actual electrical engineering, hardware development. Where now I'm 100% software development. So, University of South Carolina, electrical and computer engineering. So, if you wanted to do software, there's a good question buried here. Would you want to be a computer science major, or would you want to be an electrical and computer engineer with a software background? In my business, I think I'd rather have a really good computer engineer with a very strong software background doing the kind of work that we're doing that you see with these control systems and stuff like this. And the reason for this is the kind of software we do is tightly integrated to the hardware. It's closely coupled to the hardware, whereas sort of your generic computer science degree, they're really off in a different space doing a different thing. It's a little bit different kind of software engineering. So whether you pick computer engineering versus computer science, I think you need to look at where you want to go as a career. If you want to do something like I'm doing, I do the computer engineering with a heavy background, or electrical engineering, or something like that, any kind of engineering. I do electrical and computer engineering with a strong software background. If you wanted to get in the same business that I'm in, if you want to go develop cloud computing and AI and all this sort of stuff for Amazon, I think computer science would be a better route for you. Well, Michael's last question, I can't see I don't know if I need to scroll down or what. Okay, I guess I need to scroll.
What subjects and topics would you recommend focusing on to get into aerospace?
If you want to do software systems, the kind of the stuff that I was just showing you, again, I think electrical and computer engineering with lots of elective courses in software engineering, software design, interfacing into the hardware, that would put you in a very strong position. Aerospace, aerospace field is huge. That covers everything from the seats that you sit in to the manufacturing techniques to fluid dynamics, flutter, vibration, propulsion, AI, human factors, mechanical design. It's better to think of aerospace as what's called a hybrid cross-disciplinary field, whereas the more pure fields are like chemical, electrical, mechanical. If you kind of figure out what pure field you want, you still go into aerospace, but you can specialize in one of these other areas. Subjects and topics. Look around, see what kind of stuff you think you might most be interested in of mechanical, electrical, chemical, industrial. Study hard, work every day. kid, they used to tell me that when I was a kid. Study hard, kid. I'm like, yeah, I'll talk to you.
So any more questions or comments? Guys, this is your chance to ask questions.
I hope I'm getting some of these questions answered.
Your favorite project?
Is that a question?
Yeah, what was your favorite project that you worked on?
When I was at E-Systems back 30 years ago, we did, there are these radios, not like radios like you're used to. They're just basically just black boxes or gray boxes. And they're all pushed up into an airframe and hooked up to computers and other types of devices. And they'll put dozens and dozens of these. And this is doing for all sorts of signals intelligence gathering and stuff. I tell you, back, this is way before you were born, but it was the Western world, I guess, what was then known as the Soviet Empire, the East Bloc, and it was almost like a Star Wars kind of a thing, good guys, bad guys. They had a much simpler Earth kind of then. And just trying to get all this, not no trying, we actually did it, having to develop these things for, the Department of Defense and our nation and NASA and everybody else that was involved. Anybody in the aerospace business. It's just exciting stuff, just doing all this stuff. It's giving a really hard challenge. You got a time frame, you got to get it done. I haven't had any chance to work on any of the modern aerospace stuff beyond the F-35, nothing like I haven't been on any of the current space programs or anything. I'd like to get on the one. I think I know our company is bidding on the display systems for the lunar lander for the next manned mission to Mars, and I've thrown my hat in the ring on that one. Hope to get on. Fingers crossed. That'd be a nice little career thing to do. But I have met a lot of interesting people in my career. Y'all have never heard of Carl Sagan. He's one of the earliest people I've ever met. From him, all the way, a bunch of people all the way from then up to astronauts today, half a dozen, or about eight or nine astronauts today. A bunch of other people do cool things.
All right, guys. Who's next?
You're welcome.
All right, Ed, that looks like that may be the end of the questions. Want to tell you a great job, Ed. And as we wrap up, just a reminder that you can enter your next session by going to the email that you received from Eventbrite. Click on it just like you did to get into here. I'd like to thank Ed for presenting and thank all of you guys for attending because you guys are the future. And so, keep at it, stay strong, and enjoy your next session. All right. Thank you, Ed.
All right. You're welcome. Thank you.